All right, so what is spatial coupling? So spatial coupling, if we want to try and define it in terms of a picture, so we'll use Sudoku again. So here's our standard Sudoku. What if I decided to stretch this Sudoku out in a funny way? Now, I still want to have everything being linked, blocks of 3. So I'm still going to have this block here has to be a permutation of 9 elements. Every row of full length, and all the rows are going to have, well, not quite all the rows will have full length. These all have to be permutations of 9 elements, every column here. Now, I do have some issue here right at the end, right? These last few rows, I don't have the constraints there. So what's that going to mean? It's going to be a little bit harder for me to figure out these things at the end, right? Because I don't have as many constraints to do this. Likewise, this guy at the beginning, I don't have constraints on these columns and these rows. So if I want to try and solve this puzzle, by the way, this is a solvable puzzle. I can send you the PDF if you like these things. What I have to do is I have to tell you some of these values. If I don't initialize these values for you, you pretty much have no hope of solving it. But once I give you these values, I tell you these things, so I've given you all of them here, then it's a little easier to solve. So if we tried the peeling decoder on this and I said, all right, let's figure something out, because I have so much information here, like for example, can I get this one? So 1, 3, 5, 4, 8. Let's see. It's a 9. So I pretty much get, because I have to have so much information from these guys, I can pretty much get the value very quickly. But it continues on by induction, right? So if I was able to kind of solve this little block here perfectly, then I can actually just cut this little section off, and I again have this puzzle. So if I thought of this as a very long Sudoku, a semi-infinite Sudoku, and I just told you these first few things, you would find this puzzle wasn't very hard. You would solve, you'd work a little bit to solve this one little block, you'd cut these off, and you'd be back in the same situation. And again, it wouldn't be very hard. And while for Sudoku, this may not be a good thing, if you like hard Sudoku, for inference problems on graphs, this might be a very good thing, because we would like to be able to solve these inference problems. And spatial coupling essentially does this. So the way I'm going to define it is spatially coupled factor graphs are one where the variable nodes have a natural global orientation. So if I take all these variable nodes, there's some global structure, and they can somehow be ordered. And in that ordering, I know one of the boundaries. So I know some initial set of them in some way that's going to help me recover the other ones, so that I can recover them in an ordered fashion. So this is the concept behind spatial coupling, and this is what's going to let us do that. Yeah, so I think just this one slide vanished in my other talk for some reason. So we'll return to the correct talk. All right, so now let's do this for an Ldpc code. So what's a spatially coupled Ldpc code? Now we want a random ensemble of codes which has this global structure, and then we're going to encode with it, and we're going to use this fact that the decoding is going to work better to get a better code, or a code which decodes better in this case. And so what I'm going to do is I'm going to form my factor graph here by taking random permutations again. So I have a whole bunch of variable nodes. This dot to dot says I have a very large number of variable nodes of degree 3, whose edges go into a permutation. They go across here, they go into another permutation, and then I have a whole bunch of check nodes of degree 4. This defines my 3-4 regular Ldpc code. Now, in this particular model, there's really no reason to have 2 random permutations mapping to each other. It's kind of silly. But we're going to do something silly first. So we're going to actually do this 2L plus 1 times. So we have from minus L to L are these positions in space. So we have 2L plus 1 copies of these random codes. And at this point, of course, however well, whatever the expected performance of one code is, that's what the expected performance is of all these in a random sense. But what we want to do is we want to mix the edges slightly. So what we're going to do is we're going to break the edges coming out of this permutation into 3 edge bundles, right? So I have some large number of edges, and I'm going to take the edges and I'm going to put the first bundle here, the second bundle here, and the second bundle here. And now we can see the reason for having these 2 random permutations. And then I want to have this kind of randomly divided into bundles, and then I want to re-randomize over these sets. So now I have these 2L plus 1 sections of variable nodes, each with these random permutations, but there's some kind of global structure. If I look at the variable nodes in section minus L, they can only ever be connected to the check nodes in section minus L plus 1, and minus L plus 2. So there's kind of some local structure globally, but locally, each one of these things is also kind of a random graph. So locally, if I grab a node, it's going to look tree-like. I'm going to have these other properties that I like. Now, the boundaries also cause some issues. So when I spread edges, right, I have to add some additional checks here at the end to make so these edges have somewhere to go. And I also could think of having almost some ghost variable nodes here, which would also need to fill up these edges. But anytime I have these ghost edges, what I'm going to do is I'm going to set these variables to 0. So these grayed out variables, I'm just going to set their values to 0. In linear code, this is called shortening. So whenever you have a linear code, you can always just take some bit, set it to 0. You'll have a smaller number of code words. You basically get rid of all the code words where one of those bits was a 1. But in this case, asymptotically, it's not going to matter. What it is going to do is it's going to kind of initialize our boundary. So in the Sudoku example, right, I had to give you these 2 blocks where I told you what those values were. When I tell you these variable nodes at the 2 ends are all zeros, that has the same role. It's kind of giving me more information. And in particular, what's going to happen, so when I look at the check nodes down here, their degrees aren't going to actually be 4. So because I'm going to get a whole bunch of edges which come in here and get zeros, which effectively disappear. So some of these, when I remove these edges, some of these check nodes at the end are going to have degree 1, degree 2. They're going to be much stronger constraints. And those are going to allow decoding to get started. All right, so a few historical notes. These codes were maybe not exactly this form, but something like this form, was originally defined as Ldpc convolutional codes. So Ldpc codes were defined by Gallagher in the 60s. They're just a pure random graph where I have regular variable nodes and regular check nodes, or fixed degree for the variable nodes and check nodes. And Fellstrom and Ziegenziroff in 1999 said, well, why don't we take convolutional codes, which are a well-known thing, and make them low density? And they get something that has a similar structure to this. And when they analyzed them, it turns out they defined this kind of a decoder that was a streaming decoder. It just worked continuously, and it was very nice from a computational perspective, but it missed a very important point. They didn't initialize the boundaries. So when they would run this decoder, they pretended like the boundaries were unknown instead of initialized. So they didn't observe the improved performance. So these codes have much better performance than the vanilla Ldpc codes, but it was not observed initially. So it wasn't until 2005 where somebody set up essentially this graph and realized, whoa, these codes work a lot better than they should. So I had a way to compute this noise threshold, and they used their way they thought was going to give the right answer, and it didn't give the right answer, and it worked a lot better. And these guys said, well, turns out the calculation's not quite right. If we do the calculation another way, we get the right answer, and it's much higher than we would have thought. And so then in 2011, Kudakar, Richardson, and Urbanki, they were actually able to explain and prove why this was the case. So they wrote a proof that said, yes, when you use this kind of construction, something nice happens, and it's something that happens in general. It's not just a special case of coding or something like that. It's a general phenomenon. So these are the guys who worked on the Ldpc convolutional codes, and this is a paper. You know, at some point, everybody kind of figured this out around the same time, and they wrote a paper about it. And Rudiger, who will be speaking to us tomorrow, is part of this group. And now let's see what they did. What they did is they did density evolution. And so going back to this picture, the key thing to observe is that I can't do density evolution just by tracking one variable anymore. So that's the way that you make a mistake. You say, well, all the variable nodes are going to have an erasure probability that's fixed to some value, and I can build these trees, and the graph is regular. Because the variable nodes at the edges are actually going to have a little better performance. So what you need to do is for each position here, each of these positions, I have to track the fraction of erasure messages being transmitted from these bits, say, into this. So you'll usually think of the erasure probability as messages when they pass through a permutation. So if I average over all the messages entering this permutation, and I say what fraction of them are erased, and I call that x minus L. And I can do all the ones here. What I find out is I can write down the dynamics or the density evolution for this whole vector. So I'm going to have a vector which is length 2L plus 1, and it's a real number between 0 and 1 for each position, and it's going to represent the fraction of erasure messages entering these permutations, and it's going to be a function of iteration and spatial position. And that's what I'm showing here. So they, as people wrote papers about this, they defined names for ensembles. So this is the LRLW, and that says that all the variable nodes have degree lowercase l, all the check nodes have degree lowercase r. The chain length is 2l plus 1, so it's symmetric about 0 and has l on each side. And this w is this width. So when I break these edges coming out here into different bundles, I can choose that to be 3, 4, whatever. And so what I want to do when I want to plot density evolution now, I can't just plot a single number evolving with time. I have to plot this vector. And so what I'm going to do is I'm going to take the same code. If you remember our epsilon BP, our BP threshold was something like 6, 7. I'm going to actually choose the epsilon in this case above the BP threshold. So this is a higher erasure rate than our vanilla code can handle. So it's 0.7. And so all these guys start at 0.7, except for the boundaries start a little lower. That's why they're down here. All right. And after one iteration, it looks a lot like the uncoupled system in the sense that if you calculate this value here, what you would get for the other code, it's exactly the same. And down here, so after a few iterations. So these positions in the middle that don't feel the effect of the boundary are just obeying the density evolution equation of the original uncoupled system. But what's starting to happen is the things at the boundary are starting to perform better. And so after a little while, what happens is these guys actually converge down to the fixed point that the code would get stuck at. So if I didn't have the coupling and I ran this same analysis, I would find I get stuck at some non-zero erasure probability, and that's it. I'm not going to do better than that. And so that's about this value here. But the boundaries have this benefit, and so what happens is there's almost a wave-like phenomenon where from the outside, I learn these values in the middle based on information from the sides. And so I converge down to 0. So this phenomenon, which is termed threshold saturation, or threshold saturation via spatial coupling, shows that you can actually operate at an erasure probability above the BP threshold by using a construction which is different. So this is the key thing here. So let's see what are some properties of threshold saturation. So one of the properties these guys pointed out right away is that if you think of the degrees in your graph, L and R, now if you keep the ratio fixed, so 3 on 6, 4 on 8, all this ratios here, that's going to define a fixed rate code. In fact, all of these are rate 1/2 codes. And we can plot the BP thresholds, and we can plot the map thresholds. So what happens is spatial coupling for a large enough W achieves the map threshold. So this is particularly exciting because what happened when this result was shown was there are many things that people knew about iterative decoding that were kind of bad. Oh, I do this, and the decoder gets worse. But if I had a map decoder, I know everything would be fine. So there are a number of problems where literally you could say, oh, BP doesn't work well for this problem, but if I had a map decoder, everything would be fine. And so when Kudakar, Richardson, and Urbanki observed that what was happening is it was converging to the map threshold, all of a sudden myself and a number of other people said, all these problems where if I had a map decoder, things would work well. Let's go back and try spatially coupled codes on these problems. And it turned out on many of them, they solved them. They essentially gave now almost optimal performance. Now, the BP threshold goes down as you increase the degrees in the graph, but the map threshold goes up. And in fact, the spatially coupled performance goes up, gets better for larger graphs. So that means when I add more connectivity to my graph, I'm getting a stronger code. But if I do simple BP decoding, my decoder is not able to take advantage of that stronger code. But when I use spatial coupling, it is able to take advantage of that code, and I do much better. Now, a few other benefits. For these types of codes, there's always this question of the minimum distance. So there's something called an error floor, and these codes have a better error floor. It's kind of a detail. But one other thing worth mentioning in particular is rate loss. So when you look at this graph, what you find is that after you remove these boundaries, if you count the number of variable nodes and check nodes, you have a few extra check nodes. You have more check nodes than you would if you hadn't done this construction. And that gives you a rate loss. So you have a few extra constraints, and these constraints and their rate loss cause you some problems. So that means I need to pick a very large L to have the rate be what I would like it to be. And so in practice, not that many systems can handle that. So one of the practical open problems is maybe how can I change this construction slightly to reduce that loss due to the boundary termination. Now, threshold saturation via spatial coupling is a general phenomenon where the BP threshold of the spatially coupled system converges to the map threshold of the uncoupled system. We'll talk more about that. And in many cases, this can be proven rigorously. There's a nice connection to statistical physics. So you can think of the factor graph as defining a set of coupled particles. In fact, as much as you can say that Gallagher introduced belief propagation for Ldpc codes in the 60s, if you're really looking at very similar analysis techniques or things were being used by statistical physicists even earlier to analyze coupled spin systems, so magnetic spin systems. And in that case, for coupled spin systems, you can have order, you can have structures that fit very nicely. So in a ferromagnet, the standard model, if all the spins are up or down, that's an ordered state. Like a magnet is in some state where all the spins are oriented up. So that would be all some kind of like ordered structure. Between the BP and map threshold for codes, the system acts as a supercooled liquid. So what is a supercooled liquid? You take a bottle of water, you put it in the freezer, you wait a couple hours, the temperature goes below the freezing point of water, but the water doesn't make the transition to ice. So I imagine many of you have heard about this before or know this. We'll see a little example of it in a second. And so in that in-between phase, it doesn't have a seed crystal to help it grow into an ice crystal. So it gets stuck in this metastable state. So the analogy, which is mathematically almost exact, is that crystallization, right, this decoding, running this ordered state, does not occur without a seed, but the boundary in Ldpc codes provides a seed. Now, one example of this actually for ice, yes? So a seed is, in decoding, a seed is anything that's kind of satisfies all my constraints. So in coding, what I do is it's like I force these guys at the ends to be 0. I tell the receiver. So it's kind of like I have to terminate the code, and I have to tell the receiver how I terminated. That will act as a seed.
How do you send that information?
Oh, but because I pick a fixed pattern. So in linear codes, I can always pick zeros. So it's very easy. Yeah, for other problems, though, this could be an issue, right? So some like in satisfiability. This is crazy, right? You say like, oh, I'm gonna generate this structured KSAT problem, and I'm gonna tell you how to. I want you to find a satisfying assignment, so I'm gonna tell you there's a satisfying assignment that has these initial values, right? So at first blush, you'd say this is crazy. What could I ever do with spatial coupling for KSAT? Turns out it's not so crazy, and maybe Nicholas will tell us a little bit at the end. I haven't mentioned here. But to actually get back to this, the physics, right? Until I did this work, I had no idea this was true. I had to like look it up. So everybody knows the freezing temperature of water is 0 degrees Celsius, right? But that's actually that's like the ideal freezing temperature. It's really a better way to say that is that's the melting temperature of ice, because the melting temperature is well defined, but the freezing temperature is not. Turns out to get ice to freeze without a seed, so this is I think this is called the homogeneous crystal nucleation temperature or whatever. They don't know it exactly, but the best guess is actually minus 48.3 degrees. So what is the difference? So if you took a video camera and you watched some water freeze, if you're much above this, you'll always see the same picture. That the water will sit there, it'll sit there, sit there, and in one corner an ice crystal will form, and the ice crystal will grow from that corner out to the whole thing of liquid. That's how water freezes. But as soon as you get below this temperature and you look at the same picture, what you'll see is uniformly throughout the water, ice crystals will all form at the same time. And so it'll freeze homogeneously. This would probably be a bad thing. It probably won't make a strong crystal lattice. So why are crystals so strong? It's precisely because they have this seed and they grow into one crystal and not a whole bunch of disjoint crystals that like these things have strength. So, all right, so we have a entertainment to go with this. Fit to screen. So I don't have, see how loud this comes out.
Crystals and put them in a top, see what happens.
So I'll set this up. This is a bottle of water that has been left outside overnight. It got below freezing that night. And what this gentleman's going to do is he's going to then take a little bit of snow from the ground and drop it in the top to provide a crystal. So the water is below the freezing temperature.
Take a couple ice crystals and put them in the top, see what happens. And there you have it.
And so what we're seeing here is exactly almost the phenomenon that we see for decoding with spatially coupled codes. So if we go back here and we think about it, what we have is we have this system that's uniform, and we're kind of put a crystal here at the edge there. And then as we look at the dynamics of the system, a wave flows and causes the whole thing to converge. All right, so why is spatial coupling interesting? So in particular, it gave some breakthroughs. It gave the first practical instructions of universal codes for binary input memoryless channels, information theoretically optimal compressive sensing, universal codes for some Slepian-Wolf and Mach problems. I'm going to describe this just briefly. There's some codes that achieve capacity in some regimes with iterative hard decision decoding. So this is detail. Now this can't necessarily be proven, but codes which achieve rate distortion limits under iterative decoding is another thing. So many problems that had kind of resisted solution with the standard techniques have now fallen due to spatial coupling. So it allows rigorous proofs in many cases. So that means, what does that mean? It means that I can analyze the density evolution equations exactly and show that there's a higher threshold, that if my noise is less than that threshold, convergence occurs, and that threshold is somehow related to the map threshold. Kudagar, and Bonke have some proofs that are quite specific to Ldpc codes. We have a little more general proof we did a few years back. This is what I was hoping Nicholas would tell us a little bit about, so this is very cool. So spatial coupling is a proof technique. So that says that I want to analyze a system that's not spatially coupled, but I want to use coupling to do it. And so how do you do that? What you do is you take the system you want and you design some coupled version of it that's silly. It doesn't match the original problem at all. And then you prove that any threshold on one has to be equal to the threshold on the other. So there's some interpolation techniques that sometimes allow you to say that two systems will have the same kind of macroscopic or noise threshold behavior. And now this is what they did with SAT. So they said that I don't really want to solve coupled SAT. I want to solve random SAT. But the threshold of coupled SAT is in some sense equal to the threshold of random SAT. Now the difference is I don't know how to analyze random SAT, but I can figure out some analysis techniques for coupled SAT and prove something about that and do it this way. So this is, yeah. That's something, a very interesting point of this. All right, so now I'm going to talk about a problem, this universality for multi-user scenarios, to get a feel of what was a problem in information theory that coupling helped us do something with. And so sometimes in a multi-user problem, we have unknown parameters. And so this is in particular the case where I'm going to think about what's called a multiple access channel. So that means two people transmit to one receiver. And they have different SNRs in their channels. And there's some range of rates that are achievable for these two SNRs. In particular, when I parameterize the problem by is alpha 1 and alpha 2 are going to be kind of the amplitude of the received signal from user 1 and user 2. And I can talk about something for a sequence of coding schemes, a region of parameters where decoding succeeds with high probability in the limit. What I'm doing is I'm going to fix my code. So user 1 and user 2 are going to both use rate 1/2 codes. They're going to take code words. They're going to transmit them. They're going to pass through the channel and add together at the receiver. And they're going to get constants in front of them given by alpha 1 and alpha 2. So for fixed encoders, this is a region where I'm going to succeed. The gray region is the good region. And this boundary is the region where I won't succeed. So what I know is that if I do a low complexity decoding like belief propagation, that's always going to be worse than if I did an optimal decoding like map. Now, but sometimes there's even a maximal region of where I can succeed given by information theory. So ideally, we'd like to achieve that maximal region. And so that's what we can think of as our capacity region. So I'm going to use a very strange definition of universality here. It's attuned just for this problem. So a sequence of encoding and decoding schemes is called universal if the region of parameters for which it succeeds equals the largest one that's possible from information theory. So that's a nice thing to get, so we'd like to have that. And the channel parameters are assumed to be unknown at the transmitter. This is in fact the key element. If I knew the amplitudes that I would see at the receiver, I could always redesign my codes and make these things work. But if I want to design a scheme that doesn't know that, that was a problem that was on this list where it said, we tried doing it with brief propagation, with standard codes, and it doesn't work. We know if we had a map decoder, everything would be fine. I mean, literally before spatial coupling came out, we had a paper which said this. We know if we just had a map decoder, we could do this, but we can't. And so then I saw a talk, somebody had introduced spatial coupling. I'm like, I could try it on this problem. So I have a new tool in my toolbox. Let's see what happens. And so at the receiver, these parameters are estimated. So it's not that the unknown part is not that I don't know them at the receiver, it's that I don't know them before I transmit. So there's not a feedback link to let me know what they are. So here's this model. So user 1 transmits x1, user 2 transmits x2. It gets multiplied by this value h1 and added. I have Gaussian noise here. So I have a fixed noise variance, just variance 1, because I can always just adjust my h1s. I have a fixed rate for my codes. So this MAC ACPR is going to denote the information theoretically optimal region for the channel. So I'm going to skip that. Now, what is this spatially coupled system going to look like? So this is the thing that we'd analyzed before. We had said, let's take an Ldpc code. That's this top half of this factor graph. So I have some variable nodes, and I just have a linear code. And that's for user 1. This is for user 2. At the receiver, I'm actually going to build a joint decoder. And the joint decoder is going to include this correlation that I know what I've received is the sum of two code words. So these factor nodes represent that I've received the sum of two code words. On a side note, this is one of the reasons that people in communications theory love factor graphs, is pretty much any setup you give me, like you decide I'm going to do these funny things, I can write down the factor graph, and I can try BP decoding out very easily, and it almost always works well. So this is a problem where I took the factor graph for two problems and just combined them together. Now what I'm going to do is I'm going to couple this. So coupling, as we saw before, is we copy these things next to each other. We share a few edges. And now I have a coupled joint decoder. So this coupled joint decoder is going to have some performance. Now in this case, I'm going to use density evolution for my model. It's not for the erasure channel, so I have to do a little more numerical technique. I can't analyze it exactly. But what I can do is I can just draw these regions. I can say alpha 1 is this parameter, which is just the square of my channel magnitude. And I can ask, what's the region where decoding succeeds for brief propagation? Now, in particular, I'm going to use a rate 1/2. So this is variable node degree 3, check node degree 6 code. And it has this very funny cutout. So if the channel coefficients are large enough, things work pretty well. But the true region I want is out here, and I have this bad region. So I say, what I'll do, I'm going to increase the degrees of my code. If I use a stronger code, maybe things will get better. Actually, wrong order. I'm going to spatially couple this graph. So now I'm going to take the spatially coupled version with the same degrees. And I'm going to find that what I do is the performance fills in almost this whole thing. So I went from a very bad decoder. By switching to almost the same structure but spatially coupled, my decoder gets much better. Now what we know is that when you increase the degrees for BP, the decoder gets even worse. And so I have this giant cutout. And so this is when I have variable degree 4 and check degree 8. And I have the same theoretical region, but my thing works horrible. But now when I spatially couple it, it gets even better. And we can, in some sense, we know in this case that after we keep increasing these degrees, we'll get this whole region. So this is maybe the first problem I worked on where spatial coupling gave me something new that I could not get with standard codes. Yeah. No, that was our paper. We proved irregular codes cannot do this. That was the... so he knows the channel. So it's a different picture. So if you know these, if you want any point in this region, and I tell you I want that point, you optimize irregular codes. You're a co-author on that paper, right? No? No? Okay. Yeah. So these guys, no, a long time ago, like in the 2000s, early 2000s, they pick a point, they optimize it, it's great, it's magic. So yeah, so you can take any point you want after this. So what we actually did is we showed that if you try and achieve this point and in a corner, or like any 2 points you can't get. So like you can't even get to, but yeah. So this was, yeah, there are now many examples of problems that we couldn't solve before spatial coupling that we can now solve. This is one of them. All right. So, so now I'm going to talk a little bit about a general formulation of threshold saturation. First I have to tell you what.
Is there a reason these codes are all regular LDPCs?
So none of these codes are irregular.
Can you put your complex irregular?
So you could use irregular codes, but it doesn't, with spatial coupling, it doesn't seem there's any reason to. So we've analyzed the case. So threshold saturation still occurs with irregular codes, but in general, if you can use regular codes, you'd often prefer that. But maybe I didn't understand your question exactly. I think in general they work worse. I don't know for this exact example, but there's a case where we worked on so the generalized Ldpc codes for an optical channel, and the student I have actually proved that if you use spatial coupling and then optimize the codes afterwards, you always get a regular code. So the best choice, once you use spatial coupling, the best choice is regular. But I don't know, that may extend to this case or not. All right, so a general formulation of threshold saturation. So I haven't even quite defined threshold saturation yet, so I'm going to try and define it and explain it all at the same time. And so the key thing to see here is that we've somehow reduced our problem to the analysis of these recursions. Now, in particular for the binary erasure channel, I defined this thing called density evolution, and I said I have this recursion. If it converges to 0, things are good, because that means that all the messages I'm passing around my graph have erasure probability 0. I'm at the right answer. So, and we're going to try and reduce the whole thing to analysis of some recursion. So I'm going to think of some function f, and I'm plotting that in the red line. And this line, this blue line is just the slope 1 line. And what I told you before is if that line lies below the blue line, the recursion converges to 0. The trick with spatial coupling is actually allowing it to cross and still have something nice happen. So what we're going to see here is if we think of a discrete time recursion, so xl plus 1 is equal to f of xl, and we start it somewhere, we can figure out where we're going to converge. If we start our recursion at 1, it'll go here, and we'll find as we get this zigzag pattern down, we converge to this point. So this is a monotone recursion. What do I mean by that? So this function f is increasing. So that means that in my first step, there's kind of inductive argument that says, if I start at some value and the next value is smaller, then I will converge downward to a point. And if I start at some value and the next value is larger, then I'll converge upward. So I have these monotone sequences. And so if I start anywhere above this fixed point, I'll find that these guys converge down. If I start between these two fixed points of my function f, what I'll find is that I converge up. So that means if I initialize this to 0.5, it'll walk up that. Why is that? Because when I plug in 0.5, the next value, the red line, is above the blue line. So it goes above the previous value. And it goes all the way up to this recursion. So this is a stable fixed point. If I start close to it, I converge back to it. Whereas this is an unstable fixed point. And so if I start just a little bit above it, I'll converge up. Likewise, down here, if I start a little below this fixed point, I'll have this iteration that walks down. So what we want to do is we want to converge to 0 in this case. But clearly we can't unless somebody gives us a hint and allows us to magically start below that fixed point. We can't do it. So we're going to try and understand maybe what's going on here in terms of the structure of these solutions. So I think the easiest way to think about this is to think of this f as defining some conservative dynamics. I don't know how many people are familiar with what I mean by conservative dynamics. So in general systems, if the force is minus the gradient of a potential energy function, that defines some kind of conservative dynamics. Now, this is kind of a weird system. It's an information system. There's no mass or momentum, so we don't quite have that. But the math is the same. So if somehow the derivative in time of my thing can be written as minus the gradient of some potential at that point, then my dynamics are completely defined by some kind of energy function. And that energy function is going to tell me what's possible. And so that's what we're going to try and do here. Now, one thing I've done here is I've jumped from discrete time to continuous time, which seems like I'm cheating. But in this case, it's exactly the same. Because wherever I start this recursion, it's converged to like this fixed point or that fixed point. The same is true of this differential equation. If I initialize it up here, instead of taking discrete steps, it'll just slide down to that point. If I initialize it here, it'll slide up. So it actually, what these two equations do is identical in the limit. They go to the same fixed points. And so let's look at this potential energy. So this potential energy I'm calling U of x. So once I've made this definition, once I said I would like to have some potential energy function for which this is true, I can then just integrate it back up. Because I'm just going to say that, so I need, the way to think about it is when I'm in this regime here, the natural dynamics, since the red curve is less than the blue curve, is taking me down. If I want to push my up, I'm pushing against a force, and so I'm going to gain some energy. So when I integrate the negative of this, I'm calculating how much energy does it take for me to raise some point up to here. Now, when you get this energy function, it has a nice observation. You can think of it as anywhere you start on the energy function. So if you initialize your recursion here, what you're going to do is you're going to actually go down to some fixed point. And so, in particular, this same trick is often used to prove Lyapunov stability. And so what it says is, by setting it up like this, if I ask how is the energy changing with time, so I take my potential energy, evaluate it at this position, x of t, this setup automatically gives it its minus a square. So it's always positive. So over time, my potential energy is always decreasing. What does that mean? And it's strictly decreasing if I'm not at a fixed point. It means I will converge to a fixed point. So if I start here, I'm going to slide down to that minimum, which is a fixed point. So any fixed point here becomes a minimum here. Or if I start here, I'm going to slide down there. But from an energy perspective, we might hope to still get something to work here. So why is that? If I told you that I wanted to decode to somehow a minimum energy point, then I wouldn't get stuck here. I'd be able to jump over to that 0. So these are a little bit, in some sense, we're analyzing the recursion, and like we're trying to somehow get some physical intuition. But it's really, we're borrowing mathematics that's well known from physics and using it to analyze our case. And when I call this energy, it's not really an energy, it's the natural analog for this problem. But what we're going to find out is that as long as this energy function doesn't go down to 0, so using this definition, we'll observe a few things. The energy function is always 0 at 0. I'm also always going to assume that I have a fixed point at 0, so f of 0 is 0. And so as long as this energy function doesn't touch 0 somewhere else, we're going to find that spatial coupling can make this converge to 0 in some sense. All right. So to do that, we have to couple this recursion. So the single recursion, we can't do anything with that. It's going to get stuck. It's going to go to its fixed point. These are the dynamics. We understand the dynamics perfectly. But what I want to do is I want to change the problem. So I now want to think of updating a vector of things. And so this is going to be, this math problem is designed to look exactly like the density evolution equation for the spatially coupled code on the binary erasure channel. So I'm simplifying it slightly. So I'm just considering one recursion. We'll talk about that at the end. So I can think of a whole vector at time L plus 1 being equal to some update transform of the vector at time L. That's my density evolution operator. And I'm going to try and put this in the simplest setting possible. What I'm going to do is I'm going to assume this is a semi-infinite vector. So it's indexed by 0, 1, out to infinity. And I have this update. Now, I want to dig into this a little bit. So what does this do? This is like a messy equation. But the way to think about it is as follows. So I say that what I'm going to do is I'm going to average the right positions, apply f, then average the left positions. So if we look at the kind of factor graphs we get from spatially coupled systems, what we have is something like this. So when I want to average, so So which variable am I using? So. So let's think of this as yi. So if I think of these variable nodes, and they're kind of going to these sections down here like this. And this is like these edge bundles. So let's take this guy here. So it gets a bunch of edges from here, and a bunch of edges from here, and a bunch of edges from here. Now, if each of these, the edges out of here have erasure rate, say, x0, erasure rate x1, and erasure rate x2, if I ask what's the erasure rate of edges coming into this permutation, I'm getting the same number of edges from each one, and they're random, so I'm just getting the average. So what this equation is doing is it's saying that if I have W edge bundles, and I grab them in this fashion, the erasure probability I'm passing down to these check nodes is going to look like this average. And I'm averaging, in some sense, to the right. And so that's what this equation is doing. And now the update equation, say it's associated with the checks, this is going to be like applying the function f. All right? But now I still have to finish this recursion. I have to go back to the other side. And so when I go back to the other side, I have something that looks like this. I have some permutation over here. I have some more checks. And in this case, the edge bundles are coming back this way. And so this is grabbing, so in the second step, when I calculate this value, I'm averaging on the left. So here the key was that I'm end up averaging to the right to get a value. I apply the function f. And from the spatially coupled graph, when I'm looking at the density evolution, so these guys are passing messages with some erasure probability, and I'm averaging to the left. So then what I get is I apply, let's call this zi is equal to f of yi. And then finally, I'm going to have some k equals 0, 1 of zi minus k. So when I update, when I go to the next iteration, the three steps that occur is I first, in the density evolution, I have an averaging on one side. I apply this function, which represents the update of the dynamics, and then I average on the other side. And that's what I have shown in this equation. All right, so now, once I had the connection is this formal analysis. If I can tell you what this recursion does, then I can know what the spatially coupled system will do. So this has some nice properties. So in particular, the properties of this density evolution update operator on these vectors is it's monotone. So if I have two vectors which have a partial order with respect to point-wise, I say that x is less in the partial order if it's less at each position, then T preserves that. So that's good. Particularly because I'm going to often initialize my recursion to the all ones vector, which is the largest thing possible. So I know that the first step, if I apply, so the first step, it has to go down. And once it goes down the first time, induction shows that it will continue to go down forever. It also preserves the spatial order. So when I plot these things, if I can think of this vector as these heights, so these are going to be increasing vectors. So the xi, when I think about it, in general, the boundary is going to give me extra information. And so the vectors that I'm tracking will be increasing. And this T is going to preserve that spatial order. So what's going to happen from that is the following. When I initialize this guy to be all ones, the iterates, this sequence of numbers I get, and it's indexed by two variables. It's the spatial position I and the iteration L. It's decreasing in L for every fixed I, and it's increasing in I for every fixed L. And so we can look at this. The spatial limit will always exist. So when I take the limit, I'm always going to get to some kind of limiting value at the end. The iteration limit will always exist, so I can think about doing infinite iterations. Moreover, I can kind of iterate these and say the iteration limit, because these are continuous recursions, have to satisfy a fixed point equation. So I now know that this vector is going to converge down to some fixed point vector. And that fixed point vector, I think these L's should be infinities there too. So the infinity one actually has to satisfy the scalar update equation. It has to be a fixed point. So what I know is that when I look at these curves, in the limit, it's going to go like this. This value here in this limit is going to have to satisfy the scalar fixed point equation. So this would be like my x infinity, infinity. All right. So these are the properties I'm going to use to try and analyze this. So we can kind of see what's going to happen is that we really just have to look at this far right point. So if this whole vector is going to go to 0, which is what I want, that point has to go to 0. And if it doesn't go to 0, but I have something nice here, it's going to satisfy a fixed point equation, so there's not going to be too many possible values it can take. So I just have to see that it's not going to take one that's larger than 0. And so the theorem, yeah, time? Like done or 5 minutes? Couple minutes. All right, perfect. All right, so this is actually the last slide in that case, because the other slides after it aren't important. All right, so all right, so if I have a fixed point at 0, and it's a stable fixed point, so in this recursion I have to think about f prime of 0, and this energy function is positive everywhere but 0. So I know u of x at u of 0 is equal to 0, but it's positive everywhere else. Then there exists some w parameter, which is the width of this coupling, such that this limiting value is 0 for all w greater than that. So this is why they call it threshold saturation. You just need some w, and after that w, this thing works. And so the way it works is you define some relative potential on the vector. So you're taking this whole vector and you say, I need some potential. And what you're going to look at is it says for a fixed vector and some t. Now the key concept is that what I'm going to do is I'm going to think of perturbations where I slide this to the right. So I'm going to run my, here. So what I'll do is I'll run my recursion down to some limit. So I start it, I know it converges down to a limit, z. If this point here is 0, then I'm done. If it's not 0, it has to be a fixed point, and I know it has to be strictly positive, and it also has to be independent of w, because the single system has no knowledge of w. There's no w that comes into play. And so thus, since the energy is positive everywhere, the energy at that fixed point has to be positive. And there are two bounds you can get from looking at this carefully. One is that if you look at this sum, it's the sum of like things that are very almost the same in difference. It actually telescopes. So if I evaluate this bound at Vz1, I can get an exact value. It's just equal to the energy at z infinity, which I know is greater than 0. So the telescoping bound. If I also do a Taylor series expansion on this in T, I can show that it has to be small. So and the reason it has to be small is as W gets large, all these values that I'm looking in this interpolation, when I'm sliding this one to the right, nothing can change that much. So if I do a Taylor series expansion around T, I find that this has to have an order 1 on W term. All right, so what do I have? I have Vz greater than some constant, and I have Vz1, and I have it less than some number that I can force to 0 as I increase W. And so thus, if we pick sufficiently large W, we get a contradiction. So what does that prove? So we said if z infinity is 0, otherwise we assume it's not 0. So it proves that it has to be 0. So in this case, what we find is that using this setup, this recursion will converge down to 0. So let's go back to the picture. So here, in this particular example, since I satisfy the conditions, this recursion, even though the single system would get stuck here, the coupled recursion will still make it to 0, as long as you have something like this. This lowest energy point that's not 0 is positive. All right, so I think I'll stop there.
So is it a special coupling? I mean, so it helped definitely on making the propagation work.
Yes.
Right? But did it actually improve the actual
So no, it's like you're trying to achieve capacity. The channel capacity is somehow this fixed quantity, and you have these codes that you're trying to get there, and it gives a very general way to get there.
So just one topic, and the first spatial coupling, did the codes achieve channel capacity or not?
So you could optimize one code and get very close to capacity. So the major thing you lost was universality. So you give me a channel. You like the binary symmetric channel. I say, here's an optimized code. And you go try that code on the erasure channel, and it doesn't work as well. You couldn't do anything universally. So you could optimize for fixed scenarios, but by picking one scenario and optimizing, you would actually be suboptimal for another. So the most striking thing it gave is most things with brief propagation without spatial coupling are not universal. You have to optimize some parameters, and if you change your system at all, you need to re-optimize those parameters. With spatial coupling, there's no optimization required, and so universally, like one of the title of the paper for general channels is achieves capacity universally over all channels. And for example, the original flavor even of polar codes didn't do this. So like that was the new element in some sense.
How about the redundancy of spatially coupled codes versus that of polar codes? Is there a clear winner?
There's not a clear winner. From large enough block lengths, so moderately large block lengths, I think spatially coupled codes win. Maybe in the limit, they're both the same. They both achieve capacity. There's some mid-range where maybe polar win.
But like in the functional form for, if the gap to capacity is carried as n to the minus delta.
So the gap to capacity is pretty well understood for polar codes. For spatially coupled codes, it's not known tight. So.
Like scaling blocks?
Yeah. Well, I don't know what you mean by scaling blocks.
Do you see how much block length you need to get to?
Yeah, but it's not pinned down exactly for spatially coupled codes. It's pinned down exactly for polar codes.
But for spatially coupled, it should be better. I mean, in principle, it should be kind of.
So in fact, Marco is one of the experts on this question, and so yeah. So in principle, it should be better is a perfect answer. We believe it's better, but I don't know that we can prove it's better.
Yeah.
So 4 codes have like a 4 into 4. I mean, there's like a 4 into 4 or whatever the scale is.
Yeah, I know, but it's subtle. But the problem is that we know it for polar, but we can't prove the spatial coupled is better because we don't know it exactly. We're pretty sure it's better.
So Ldpc codes in general has much better. I mean, if you don't care about capacity, I guess.
They have better scaling.
Then it's
Yeah.
much better.
Yeah.
But when you're close to capacity, it's a different story.
All right, so.
You have to pay because, I mean, you're giving the seed, right? So you have to pay for that.
So in the interest of time, we should probably take this discussion off.